So we should do some more examples of integration. Here's one that shows off what's going on with when you have bounds of integration. For a substitution, there were some special rules that you have to follow when you're doing a definite integral, when there are bounds of integration that you must change for the substitution. When you're doing integration by parts, they're not as big of a deal. There is a thing that you want to do. The regular integral by parts formula is the integral of u dv is uv minus integral v du. If you have bounds of integration, if you have a definite integral, meaning if you have the little numbers on the integral symbol, the way this changes is the new integral is also the integral from the same bounds of integration. And the first part, the part that you've already integrated, well, when you've already integrated it, the thing you have to do after that is plug in those numbers. Being able to write this down is really convenient to be able to say, here I'm going to have to plug in the numbers after I integrate. Here I'm ready to plug in the numbers now. If you plug in the numbers now, then it stops being a gross expression you have to write down over and over and just a number maybe. That can be convenient. Here's an example that shows off some of this. If I have the integral from 0 to 1 of, let's do x times 2x minus 1 cubed dx. It's probably worth noting that you don't need any fancy tricks to do this problem. Integral by parts might be overkill because you can FOIL out this cube. If you FOIL out 2x minus 1, 2x minus 1, 2x minus 1, that'll eventually just be a polynomial. We know how to integrate polynomials without integration by parts, but sort of a lot of foiling, and knowing the tricks to get around that can be convenient. So we'll do this by parts. Same deal as before, u equals x is a nice choice of u if you can handle it, because the derivative of x goes away. That's what we're hoping for when we do an integral by parts. If u is x, then dv has to be everything else, so that's 2x minus 1 cubed dx. Du will be the derivative of x is 1 dx. V will be the integral of this thing, which is annoying unless you've gotten pretty good at that substitution trick. This is a baby substitution. 2x minus 1 I can read as being just x. This is something cubed. The integral of something cubed is 1/4 something to the 4th. But if I took the derivative of this with the chain rule would poop out an extra 2. We put a 1/2 here to cancel it. This is the exact same as when we were integrating e to the 3x and got 1/3 e to the 3x, or maybe the number wasn't 3. I don't remember, but it's the same type of deal there. The derivative of 2x minus 1 is just a constant. We can fix that constant doing what is basically that substitution all in one step. So our new integral, our integral formula is integral of u dv equals uv x times 1/8 2x minus 1 to the 4th, evaluated from 0 to 1, minus the integral from 0 to 1 of v 1/8 2x minus 1 to the 4th du is just dx. So now I'm at the same type of integral again. This is a really common thing in integration by parts. It's not a hard and fast rule, but very often the new integral you need to do after the parts is basically the same as the old integral you did to set up the integration by parts. It's very often that those come out the same. Anyway, I want to plug in 1 to this. I'll get 1 times 1/8 of 2 times 1 minus 1 is 2 minus 1 is 1 to the 4th. Minus plug in 0, you get 0. Minus, I still need to do this integral. Same deal as last time. This is the integral of something to the 4th. I add 1 to the exponent. I get to the 5th. But now I need to divide by that new number. 1/8 divided by 5 makes a 1/5, and then I also need to divide by this 2. So I get 1/2, 1/5, and 1/8 all out front. This I've integrated but still haven't plugged in. I need to evaluate this from 0 to 1. This number is 1/8 minus 0 minus, I'll put it in brackets, plug in 1, what do you get? First off, this number out front is 1 over 80. 1 over, not 18, 80 Plug in 1, you get 1 to the 5th. Minus, now plug in 0. 1 over 80 times negative 1 to the 5th. So I got 1/8 minus 1 over 80. This is a negative 1, combines with that negative 1 to make this a plus. So I get another minus 1 over 80. Common denominator is 80. I got 10 over 80 minus 2 over 80 gives me 8 over 80. Comes out to be 1/10. For definite integrals, don't forget your calculator is able to give you digits on this. It's pretty easy to confirm that those digits are 1/10. Don't fool yourself into thinking that plugging this into your calculator and getting those digits is going to be good enough for the exam. The exam is about, have you learned this integration by parts stuff, even when your answer is just a number. There's an integral by parts with the bounds of integration. Here's an example that kind of mixes up what's going on. If I wanted to integrate x natural log x. We've been doing a ton of examples where using u equals x is a great idea, so let's try that out here. If u is x, then dv is natural log x dx. du is derivative of x is 1 dx. v is the integral of natural log x is... Wait a minute, I know the derivative of natural log. I don't know the integral of natural log. Uh-oh. The good news is most of the time when integration by parts fails, it fails in this way where you can't do the little integral, which means it fails real fast, which is good news if you don't want to spend a lot of time going the wrong direction. It's not like substitution where you can almost always get through the substitution. The biggest problem with parts is usually that you can't do the little integral, and you usually find that out right away. This is an example where you don't want to let u be the x thing. Remember, the goal of our u is we want it to be something that when we take its derivative, it goes away. Well, there's no better example of that than natural log. Natural log is kind of a gross function that we don't like having to think about. If u is natural log, dv must be everything else is x dx. And the reason u equals natural log is such a great idea is because the derivative of natural log is 1 over x, doesn't have a natural log anymore. Natural log kind of just evaporates and gets easier when you take its derivative. V is now the integral of x. I know that. It's half x squared. I could put plus a constant. I probably don't want to. Cool. What does this turn into? The integral of u dv becomes uv ln x times 1/2 x squared minus the integral of v du, half x squared times 1 over x dx. A lot of people now go crazy and try and integrate this by parts. You can't do this times this. That's not how the product rule works. You can't take the derivative of the one times the derivative of the other. So it doesn't work that way for integrals either. There's a whole product rule and it's gross. We're now at a place where things have gone good. Students very often don't notice the things that have gone good. The thing that's gone good is that x squared times 1 over x reduces. If I rewrite this in a more natural order, the constant out front, and then the simple function, and then the messy function. This becomes the integral of 1/2. X squared times 1 over x is just x. Combine those, simplify it. Let it look like something you know how to integrate. What's the integral of half x? It's half integral x, or you add 1 to the exponent, divide by that new number. Boom. We did the integral. Moral of the story is you usually want the simple polynomial function to be the u when you do parts, but when you don't, if you see a natural log, you almost always want to use that as your u. This works even to the extent that if you have the integral of just natural log x, try letting u equal natural log x. And dv is everything else is, there's nothing else, just the dx. dv is just dx. I think this is a homework problem, so I won't work this one out now, but this is the right way to integrate natural log x, which, by the way, could be a thing you tried here when we said, hey, I don't know how to do this because I don't know how to integrate